Okay, cool. So now let me just share my screen. Okay, so I hope you can see the screen now, and let's arrange these things a bit. So today, you might have seen from Moodle also that we will talk about three things, so to say. First, we will have a brief look at the theory, at logistic regression from some theoretical views, some theoretical aspects. And then, secondly, we will have a look at lab 3. And if time allows, we will have a look at lab 4 also. So let's move to the first thing. I will probably turn off my video just so that the internet remains smooth and the connection remains smooth. Okay, so this is the first thing that we want to talk about. You guys have already had a look at logistic regression in during the lectures, and here we will just have a brief look at the loss function and see different views into that, and then we will have a look at the case where the data is perfectly linearly separable. Okay, so first, just some brief insights into the loss function, and before moving to that, just let me give a brief definition to you guys. There is a function in machine learning in particular, and also of course in general, that we name as sigmoid function. So this function actually maps from real value to 0 and 1. I mean, we can use this notation also, because in the limiting case it gets to 1. But if we exclude infinities from real, then it maps to this open interval 0 and 1. So the function is like that. So this is x, and this is sigmoid of x, okay? And it is defined as, we can define it like that, or if we simply divide both numerator and the denominator by e of x, then it becomes 1 plus 1 over e power minus x. So these are both valid definitions of this function. Now coming back to the loss function. So the logistic regression loss function, as you can see, is given by, you can see this on left hand side, right? The first equation. We have also seen that in the tutorials. So for all, we sum over all the samples, and we have log of 1 plus exponent of minus yi w transpose xi plus b. This is a loss function, and you might also remember the homogeneous case that Martin discussed, and this case refers to the fact that we can actually use we can actually combine these two variables w and b in one variable, that is like that. And similarly, we can say that now we can also join x in this form by appending simply a constant one in the last dimension of the new vector. And in that case, we can see that now, if we say this is equal to w bar, let's say, and this is equal to x bar, then we can say w bar transpose x bar is equal to I mean w transpose b x and 1, which is equal to w transpose x plus b, right? So we, without loss of generality, we will only refer to this case, and we can always derive the case where we have a constant from this homogeneous case. Okay, so in the tutorial we will only refer to this homogeneous case. So in that case, we can rewrite our loss function. This loss function can be rewritten as log 1 plus exponent of minus yi W transpose. Well, I will not use W bar again and again just for notational convenience. We will only stick to this W and X. Okay, I won't use W bar and X bar, and we will just consider that this is a homogeneous case, and we can already see that the non-homogeneous case where we have a constant B that can be derived like that can be dealt in the same way as the homogeneous case. So that's why I will skip this W bar for notational convenience. So we get W transpose xi. So this is like now a simplified form of the loss function of logistic regression. Cool. Now, just again for notational ease, I say that this is equal to z. So zi. So yi W transpose xi is equal to zi. We can see that we have this W transpose xi and this will be a scalar. So that's why this I have written zi as scalar, just to show how this function came from the original function. And now we have I is equal to 1 to n log 1 plus e power like e of minus z. Yeah, e of minus zi. Okay, so just to see it in a simplified form, and we can also use like we can also invert this log by using a minus outside, and now we have 1 over 1 plus e power minus zi. Okay, and now we can see that this is actually the sigmoid of zi, right? So this is just to show you guys that we can also think of the loss function of logistic regression in terms of sigmoids. So now this function becomes log of sigmoid of zi. Okay, so this is just one of the insights that I wanted to give you guys. Then the next thing is about the gradients, so to say. And I guess you guys, of course, are already aware of vector calculus, and you can already compute this gradient as you can see on the left hand side. This should not be much of an issue. What I want to comment on is this second last term of the gradient with respect to b. In fact, let's stick to the gradient with respect to w, because we have seen we only stick to the homogeneous case, and you can already see that this is also uh, the sigmoid form. So this we can say that this is equal to e of z over 1 plus e of z, right? So this is again in the form of sigmoid. So this is one of the good things about the loss function, that the actual loss function as well as the gradients can be viewed in terms of sigmoid. So this is all what we wanted to talk about in terms of the loss function and the gradients. And we will actually now jump to this case, the second case, where we say that what happens if we perfectly train our logistic regression in the case where the data is linearly separable. So let's come to that. If you guys have any questions till now, you guys can ask me, otherwise we will proceed. Uh, so it seems we have no questions. You guys are with me, right? You guys can hear me. Just give me a quick thumbs up so that we can proceed. Cool. Okay. So now we talk about the case of perfectly linearly separable data. So what do we mean by that? When we say linearly separable, this means some data, like some data points where we can draw a linear boundary to separate the two classes. Suppose here we have these two classes, one is represented by dots and other is represented by um this cross, right? And you can see that we can draw this line, which separates these two classes. This is what we term as linearly separable. So, like if let's say if we had this dot here, then it won't be possible for us to linearly separate this data. So this is the case now that we will be dealing with, and in general form, it should be something like that. This is what we are referring to 2D case. So, like let's say we have classes like that, and this is like a linear line. I mean, this is the line that is separating the data. But now the thing is, this line is not passing through origin. In that case, like we need again to have a look at this constant b as we just saw. In the loss function, but we won't deal with this case. We will stick to the homogeneous case. Okay, and we have already seen that this non-homogeneous case can be derived or can be also viewed by expanding this homogeneous case. So we will stick to that. Now what happens if we have a data that can be like that is in the form of two classes that are linearly separable. So the our claim here is that in such a case logistic regression fails. Okay, and how it fails, we will let's first, like, let's have an insight into that. So the loss function was defined as L is like L of W is equal to summation over all samples log of 1 plus exponent of minus yi w transpose xi. So this is the loss function that we want to minimize, right? Now there is one thing that comes from like from the concepts of geometry. It's not that hard actually. So the thing is this W transpose Xi, right? We will have a look at this. We know this is a scalar value, but this is a bit more than that. In geometrical terms, this is actually the signed distance of X from the hyperplane. Okay. So usually, like in maths, we define a homogeneous hyperplane. Like if a hyperplane is passing through origin, like this one, we will define such a hyperplane by an equation which is given by W transpose X is equal to 0. Okay, so we can define a hyperplane by an equation like that. And what is W in this case? This W is actually a vector which is normal to the hyperplane. Okay, now in 2D case this hyperplane is a line. In 3D case this hyperplane is a plane, so to say. I like, just for you guys, let's see if I can draw that, and just to give you guys some idea, like it will be something like that, so to say, right? So this is the 3D case where this hyperplane is actually a sort of an infinite plane that is cutting like a 2D space, so to say, in this 3D real world in R3. So let's come back to the 2D case. So just for insights. So this W is actually a normal perpendicular to the hyperplane. And the the way actually that we usually define hyperplane is we give the normal vector. So we don't not only talk about W, but we talk about the W where the length is equal to 1. So this is the normal vector, right? So the normal to any surface is the vector, of course, that is pointing out or like in one direction or the other. It depends upon how it see, and its magnitude is 1, right? So this is the way we define a plane. Okay, so this and in other in parallel, we can also look at this line as the decision boundary between these two classes. Like let's say this is the class number 1, this is the class number 2. So this line can also be seen as a decision boundary. So whatever falls on this side belongs to class number 1, whatever falls on this side belongs to class number 2, right? And whatever falls on this line falls on the decision boundary. So the points that fall on this line have a special case where wx will be equal to 0. For the points of class 1, they will fall on one side, and for the points of class 2, they will fall on other side. And if we go a bit further, for the points that belong to class 1, like this, the next thing that we will now talk about is the distance from the hyperplane. And the distance from the hyperplane is actually like, if we want to calculate the distance of any point from the hyperplane, let's say this point, the distance will be given by the shortest distance from the point to the hyperplane, and of course the shortest distance will be the perpendicular, right? So if we allow perpendicular line to fall from the point to the hyperplane, this will be the shortest distance from the point to the hyperplane. And this is what we will say, that this is the distance from a point to the hyperplane. Right now these red lines show the distance of the points of class A from this hyperplane, which is defined by w transpose x equal to 0. Similarly, green lines show that for the points of class number 2. So we will see, like we can see that for the points, if let's say if this w is in this direction, in that case we can say that, like talking about the same example, we can see that w transpose x is greater than 0 for all x element of class 1, right? Similarly, w transpose x, I mean w transpose x is the dot product, right? So if they are sharing some direction, their dot product is greater than 0. Similarly, this is less than 0 for all x that belong to the second class, right? So this was greater or less than 0 because we assumed that our w is in this direction. If it were in this direction, then we would have this greater than and less than will be reversed. So this is the second insight that we now have, that this W transpose X can be also looked in geometrical terms, where W transpose X is equal to 0 defines the homogeneous hyperplane. And for any point xi, W transpose xi is actually the distance of that point from the hyperplane, right? So when now what happens when this X is so to say linearly separable? So before going in this direction, there is one last point that we need to talk about. We have also claimed that, in fact, we have also observed that this W transpose X also serves as the decision boundary, right? So let's also add this, that X, yeah, so X, all X such that W transpose X is equal to 0. This is the decision boundary, right? This is the equation of the line actually, right? W transpose X is equal to 0. This is the equation of the line here, like the hyperplane in 2D. So this is the decision boundary. Another, like one thing that we can observe here, that if we multiply with any constant here, let's say this constant C, any constant, the decision boundary will remain the same, right? So because this W transpose X is equal to 0, so this set will remain the same as this set, right? So multiplication with constant won't affect this decision boundary. This is the thing actually that leads to the problem in case of linear separability. And now we are coming to that. So what happens is, we can say that we can choose this W as large as possible, right? Because if we have a look at the loss function here, if we have a look at this loss function, what we want to do is, when y is positive, we want to have this W transpose X as large as possible. And when y is negative, we want to have W transpose X as small as possible, right? And since there is no bound right now on this W, we can choose W really large, so that for positive X, this W transpose X will be large, and for negative X, this W transpose X will be really small. And this is where the problem happens. So if we have a look at the function once again, the function was summation and we have log of 1 plus, right? So this was the loss function, right? Now let's see what happens if what is the minimum value of this loss function. This if the minimum value of loss function is achieved when, of course, we have a minimum value of this term, and this is achieved when we have here infinity, because then it will be multiplied by minus, and we have minus infinity, and e to the power minus infinity, we know it is equal to 0, right? So right now we can see if we choose w is equal to infinity, let's say, right? So then for all the points, I mean, if we choose w really really large, then for all the points that lie on one side of the line, we will have w transpose x. I mean, of course, w is a vector; it's not a scalar value, but this can we can choose w so large that w transpose x can lead to infinity for the points belonging to class one, and for the same w, of course, for the points belonging to class 2, it will lead to minus infinity, right? And then we multiply this with y, and then we have a minus here, and as a result we get e to the power, like this whole thing approaches e to the power minus infinity for when for large enough w, right? So as a result, this whole thing approaches 0, and we are left with summation I is equal to 1 to n log of 1 plus 0, which is equal to log of 1, and which is equal to 0 in the end, right? So the problem here is there is no check right now. We cannot stop this from happening. If the data is linearly separable, we can choose w as large as possible, because mathematically to uh, we simply want to minimize this function, right? And if this data is linearly separable like here, in that case we can simply choose w as big as possible, and the function will be minimized more and more and more, and the function will reach its minimum value when it is equal to 0, and this will happen when w transpose x is equal to infinity for one class and minus infinity for other class. So this is, I mean, we of course minimize the function, but we didn't get anything out of that. I mean, it's not worth it. This is not what we were looking for. We were looking for some point that we can actually make use of. We cannot make use of a point like that. So this is one insight into the problem. And now there is another rather theoretical way of doing that, as we can see here in this solution. Actually, this is also coming from the same insight that we just discussed geometrically. Here we are just sort of um, architecting the proof in a different way, but the insight is the same. So the way we proceed is, we say, okay, if okay, in fact, let's stick to this homogeneous case, and let's have a look at this proof on paper. So second way, case of linear separability. Okay, so let's look at it second way. So what we have is, suppose we have a minimum point w star. In that case, we know if this is a global minimum, then L of w star is less than, if this is a global minimum, and if this is strictly global minimum, then this L of w star is less than L of w for all w, right? Or if it is not strict, I mean, we can also say it is less than or equal to w. So what we say that this w star minimizes the loss function, right? This is the definition of the global minimum. Now we have seen that this L is greater than or equal to 0, right? With equality, in case when y I w transpose xi is equal to infinity for all I. This is what we have already seen geometrically, that this function becomes strictly equal to zero only for this case which is not desirable. Okay, so we say okay, we don't need this case. We suppose that our L of W star achieves some value greater than zero. Okay, that is strictly greater than zero. Now we assume that this point exists for linear separable case. Okay, this is our assumption. We assume that such W star exists for linearly separable case. This is our assumption. If this assumption holds, then we are good to go. If it doesn't hold, then we prove in a contradictive fashion that we cannot like this linear separable case is not cannot be solved by logistic regression, so to say. So this is our assumption. Now, what now? Just for again for notational convenience, we say okay, zi is equal to yi w w star transpose xi, right? So this is again just for notational convenience. And now we say okay, if the case is linearly separable, then we have loss of then we can say L of HW is equal to, we know that it is equal to I is equal to 1 to n log 1 plus minus HZI, right? And this is less than L of W. In fact, here we have L of W star. Yeah. So this is less than L of W when H is greater than 1. So this what we are saying here is that if we multiply, if like we have defined a sort of a function L of h, like this is again actually this is just the definition of the loss function, but we have a constant h here. When it is greater than 1, this result will always be less than L of W because the case is linearly separable. We have already seen that if the case is linearly separable, multiplying multiplying the decision boundary with a constant will not change the decision boundary as we have seen here. However, it will of course change the values. Uh, However, it will of course change the values W transpose X for positive and negative classes, right? It will push them towards positive and negative infinity. So this is what we are saying here, that if we multiply this zi with a constant which is greater than 1, then the resultant value will always be less than L of uh, W star. And in fact, this thing approaches 0 when approaches infinity. Or like we can write it in a sort of more formal way. When h approaches infinity, L of HW star approaches 0. Oh, I'm sorry, is equal to 0, right? So this is now the problem. The problem here is we have already seen that whenever we have h greater than 1, our new value of loss function becomes less than L of W star. And we claim that L of W star, because W is a global minimum, we claim that this should be the minimum, right? So these two things generate contradiction, right? So what again in other terms we can say that for any epsilon here, like if L of W star is greater than 0 by a value epsilon, and if the case is linearly separable, we can always find another W star which will be equal to h of previous h into previous W star. So we can always find another h so that this h into W star will lead to the value of the loss function being lesser than the value for W star. So this means W star was not the global minimum. So the global minimum, so to say, will be achieved when we have w large and when we have either h going to infinity, which is like a case that is not beneficial for us, or well, of course when w is in such a way that w star xi is equal to infinity for one class and minus infinity for other class. So because of this contradiction, now we know that this is not possible, right? So now we know that this is not possible. The thing is, if you see these notes without the video, you will see, okay, this step, and now you will see this step, and I have written not possible, and you will get confused. But if you see this with the video, you will understand that this was written afterwards. So not possible in linearly separable case. So I would recommend that if you have a look at this whiteboard, you look at this with the video. So you see, in both cases, we dealt the problem in the same way. We claimed that okay, having a constant here or like C here or H here does not affect the decision boundary, but we can always select a constant large enough so that the values become positive and negative infinity for positive and negative classes, so to say. And as a result, the loss function reaches zero, which results in a case that does not solve logistic regression. So this is how we can like have a look at this problem of linear separability into through like two different aspects, which ultimately merge into the one, so to say. So if you guys have any problem, like any question till here, you are welcome to ask me. Otherwise, we can proceed. So are you guys with me? If you guys can hear me, just give me a quick thumbs up so that we proceed. Okay, I can see one yes. So I okay, two. So I assume you guys can hear me then. So is the loss function still working? Uh, can you please unmute yourself and ask this question? I haven't understood your question completely. Okay, maybe I I will try to answer this from what I have understood. Is it a valid loss function since we cannot find? No, of course. That this is the thing. This loss function seems to not solve the most like the simplest case that we can have for logistic regression, because yeah, let's actually we are getting to the remedy of this problem. The loss function now in its current form is not solvable, so to say, because we have already seen that we cannot like get anything useful. We cannot get any useful value. Like we are getting this w reaching infinity, and this is not of course useful. So this loss function of course won't solve the problem of logistic regression in case of linear separability. So what we do is we actually, okay, before going to the remedy, just one more insight. If you see a non-separable data, like we just saw above, like this, right? So what happens in this case is whenever w grows to a certain proportion, I mean, of course, the loss function now wants to have as big values on this side as possible and as small values on this side as possible, right? But now the problem is we have this we have this point that is lying on the wrong side of the line, right? Now what happens is when loss function, like when the w grows to a certain extent so that this w transpose xi becomes greater for this side and becomes less for this side, when this value starts growing to a certain extent, this value keeps this growth in check. Okay, so what happens is if like if this value becomes negative, quite negative enough for these samples on this C2 side, there will come a point when this value will grow so much that the loss function now uh, won't be minimized further. In fact, the value will start increasing now, right? Because as we saw from this sigmoid case, we can see that the growth or the decline is most in this region, right? So as x reaches this region, the growth really slows down, right? So if this point probably has such an effect like a gradient or an effect like this, and this point when it grows enough, like when this value becomes negative enough, this point has an effect something like this, right? So the delta here, this delta here is relatively less, and this delta here is relatively large. So the effect of this point on loss function becomes greater compared to the effect of these other points on loss function. So this, if this data is not linearly separable, then we inherently get a check, we inherently get a regularization, so to say, which stops W from getting these degenerate, or I mean, or these trivial values, so to say. But when data is linearly separable, of course, we don't get this inherently. And now we need to introduce this thing explicitly. Okay. And a common way of introducing this is that we add a value to the loss function. Here you can see from this line that I have highlighted on left side of the screen, we say, okay, we want also like this loss function not only should minimize these distances, but should also minimize the norm of of the vector that we are training, right? So this W, I mean, if we here it writes W square plus B square, but again, in homogeneous case, it will be L, let's say head of W will be equal to L of W plus lambda into W square, no, magnitude of W squared. So now this thing sort of explicitly introduces this regularization that we had implicitly to some extent here in this non-separable form. In separable form, this comes from introduction of this magnitude scared. We now the loss not only wants to minimize the distances but also the magnitude, right? So you see, this is actually, again, we can also draw this motivation from this case of this geometrical case, that actually when we define this when we define this hyperplane, we talk usually in terms of normal vector, right? Right now we had here W, and there was no restriction of W. W could grow, or could, like, the components of W could reach up to infinity or could decline up to minus infinity. We had no check on that. Usually when we, I mean, when we have the definition of hyperplane, we talk in terms of normal vector, and in normal vector we already have this compulsion that this is the definition of normal vector, that its magnitude should be equal to 1. So this is sort of something from where you can also draw this motivation, that that's why we want to keep the norm as small as possible. Now the loss function sort of and this is a hyperparameter of the algorithm. We can, this is something that we need to tune ourselves. This is not something that algorithm will tune. We can check for different values of lambda and see which value gives better results. So this is why we have these training sets and validation sets and test sets. I guess we need to talk about that also sometime. Yeah. Okay. Anyways, maybe let's see. Maybe next time. Hmm. Okay. Let's see. So now we have seen this problem of regularization, the problem of linear separability and how to solve that. And now, if you guys have some questions, please let me know. Otherwise, let's have a 4 minutes break. So it's 10:26 now. Let's resume at 10:30. And I will pause recording now. Resume. Okay, so now let's start the next part of our tutorial, which is related to the labs. And the first thing, we will first have a look at the lab record related to data preparation, and if we have time, we will move to the fourth lab. So this lab is relatively easy. So what we want here is, we have, like, as I have sort of given you a brief overview here, we have an HTML, we have some HTML text which is in the form of strings, Python strings. We load that, and after that, like, these are all the pre-processing steps, right? So we need to pre-process the text so that it is in a form that is more useful for machine. Okay, now this thing more useful is very loose, and this, like, the things like it is valid, it is useful, and it doesn't help, it helps, like these words, the thing is, depending upon different contexts, these words can mean different values. That's why this is rather in loose context that I'm using them. So, for instance, like for pre-processing, first thing what we are doing here is we are removing the tags. So, since the data is in HTML form, like, and those of you guys who maybe have some knowledge about HTML, like there are different tags. Like there is some tag P for paragraph, there is tag this BR for new line, and there's some tags for bold and things like italic, things like that. Div tags, class, anyways. So I mean, there are a tag for link, things like that. So first we want to remove those tags. Secondly, we want to remove the punctuations. Then we want to convert all the data to lowercase, because of course for machine, lowercase and uppercase means different values. Then we split the data in words, right? So we break our data at every space. And then lastly, we remove unnecessary words. So you see, I mean, this what we are terming as pre-processing. In modern deep learning based approaches, this these are the things that might give a lot of information, right? Modeling these things properly might actually enhance the results. But for simple models that we will see in our labs, these are the things that probably will reduce, will sort of decrease the efficiency of our algorithms. So that's why we remove them. And when we say unnecessary, as this is why I have to place this question mark also. So actually nothing is unnecessary. This is just that for some algorithm, it gets biased because of some words. For example, the word the, this might not convey that much information for simple algorithms, but for really complex and really efficient algorithms, uh, this word might add to the context, that this is the book that I was talking about, for instance, something like that. The algorithms that are able to capture the context from the sentence, for them, it might be really helpful. But we will stick to the simple case as we mentioned. That's why we will just have a look at how to pre-process the text data so that it is in the usable form for the simple algorithms that we will have a look at. So for that purpose, uh, I guess we can skip, like, we won't have this PDF open in parallel, because we have always written all the questions on top. So I guess we need not have a look at the PDF in separate. In fact, we will have this um, whiteboard in parallel open. So the first thing that we want to do, like, there is a TSV file. It is equivalent to CS. It is just like CSV file, but it is tab separated. So we read TSV file and load all the values, and then uh, we just have a look at different values as it was asked in that one of the tasks. So we see how the values appear, like what is the value for a zeroth index at 0, 1, 2 sub indexes. So this seems like some sort of ID, this seems like some sort of value, and this seems like all the data that we need to parse and pre-process. Like you can see here the tags, you can see the punctuations, you can see caps, like small and capital caps, and you can see the words like like this the and things like that. So we need to pre-process this data a bit so that we know so that we can deal with it properly. And we have this exclamation marks, these three dots, yeah, all the things like that. Like a better way of displaying this data is using this Python like this pandas, and we can this always use this head for any pandas data frame. We can use dot head, and it will print out 10 here, like it will print out 10 top columns, like 10 top series data ranges from this data frame. And we can see that this is id, this is sentiment. Sentiment means whether this review is positive or negative. So that now we get a sense that the data set consists of a list of reviews, and we also have sentiments. So we can treat this thing, this review text, as x, and this sentiment as y. Okay, and this id is just to make these reviews unique. We don't probably need to have a look at these ids. So the next thing is to remove the tags. And for that, we use this beautiful SOAP package of module of Python. And this is really helpful for parsing. Also, those of you who might have worked with Python and scrapers might already know that. So as an example, we just load review 0, and we get this function get text already removes all these HTML tags, and you can see now the text is tag free. The second thing is to remove the punctuations, and for that we use regular expression. Now, regular expression is actually sort of a complete subject in its own. There are like ways, there are rules that we need to follow while writing the regular expression, and actually we don't like this is, sometimes we, let's say we have a long string, and sometimes what we want to do, we say okay, replace, let's say hello. Let's say we want to replace with hello with exclamation mark everywhere. Okay, this is a simple case. But sometimes we want to replace patterns, like we want to say okay, we want to replace all the values where we have I don't know, let's say we want to replace all the values where uh, um I mean, where, yeah, I mean, we can search for all sort of patterns. Like we can remove, let's say we want to search for all the values where the numeric values are greater than 10,000, so to say, okay? And all the values uh, where that are abbreviations, so to say. For instance, if we have something like for example, let's just for an example, like it seems like a abbreviation because we have some small caps, some big caps, and things like that. It is difficult to use this this replace function here. So we need to replace the patterns. So I won't go into the detail. I will just tell you what it is doing. So what this part says is we are looking for the pattern from small a to small z. Like we are looking for all the letters from small a to small z. And now then we are looking at the letters from big A to big C. So in other words, we are looking at all the alphabets, okay? And then when we use this thing, this means that we are negating, right? So this is like the inverse of everything here. So what does it mean? We look for all the things that are not alphabets, okay? And we replace them with a space. That's what's happening here. That's why this variable is named as letters only. So as a result, we get this thing. You can see that all the punctuations and dots, like commas, etc., all the things are gone. After that, we need to convert to the lowercase as the next step of pre-processing, and this is also very simple. Just call this dot lower function on the string, and it will convert everything to lowercase. And then the next thing is to split to words. And for this, we simply call split function. If we don't give any parameter here, it will understand, okay, we need to split the string at every space. So this is the lowercase form of the string. And after that, we just printed out the first word so that you can see that this splitting is working. So this is the first word with, and it is printed out here. So now we have the words ready in the list of lists. Sorry, not list of lists, but in the form of a list of words. Now the next thing is to remove the unnecessary words. Now, this is again, as I mentioned, this just depends upon the context and the power of the algorithm that we are using. For simpler algorithms, these words actually bias them towards wrong results. So we need to remove these words, and the way to do is it. This is also mentioned in the exercise sheet, by the way. We load this NLTK package for natural language processing. This is also a very common module, and then we download the stop words for English. I mean, here we download all the stop words, and then we imported them, and then we filtered out the English stop words. And when we print them, we can see that these are the words that are sort of referred to as the stop words for English language. So these are the words like that probably, I mean, according to this package, let's say, don't contain any useful or yeah, the information that the words that we can remove during pre-processing. So that's what we will do. So to now we will join all these steps. Okay, so that's why we make this function review preprocessor, like so to say. So review prepro is the name of the function. We give the data, and we give optionally we give an option of using the stop words if we want to. So we are exactly just joining all the steps we saw above. We are we remove the text, we remove the punctuations, we convert to lower form, and if there is some remove words list available, we use we exclude our word exclude the remove those stop words from the list. So what we are saying here is W for W in words, like include all the words if W is not in stops. So if W is not in stop words, um, then we use this W, otherwise we don't. I guess there is probably an error here because we want to use here stop words, not stops. Yeah. So I guess this is wrong. So we need to have stop words here. So after that, because stops is not defined simply, right? Yeah. So afterwards, yeah, I guess this worked because we had loaded stops already in the step ahead. That's why it worked. So we can also live with stops because we are simply like this will simply use the global value of stoppers. So now we have, in fact, this is the way it should be because this should be true or false. This should not be a list. So we say if if there is stop words is true, then we remove all the words that are here. Otherwise, we keep all the words. And after that, we join that list of words. We join all the words in the list by a space. And now when we run that, now what we are doing here is we first like just declare a empty list, and for all the like we get the number of reviews by this dot size argument, and then for all the reviews we simply append this we give the review number I to this function, which will do all these steps and give us the clean review. So that's what we are doing here. So yeah, remove stopwords is true. So stopwords will be removed. And now we have generated this list of clean reviews, so to say. Once we have that, now we use this bag of words approach that we have already talked about in the lecture. For that, there are actually quite well-made functions, quite well-made classes in sklearn, scikit-learn. For example, this count vectorizer. I mean, you can of course search for that. Where is that search? Search. Anyways, yeah, you can simply copy that, and yeah, yeah, search Google for count vectorizer. You can use that like anyways the way you want to. So this is like the count vectorizer class, and I would really recommend you to go through that because it will sort of enhance your knowledge a lot about how different steps of preprocessing work and how we convert this text to a vector form, so to say. So here we say, okay, we will use a words analyzer. We will not use a tokenizer. We have already done preprocessing, so we won't use any when we have already used top words. And here is the number of features that we want our vectors to have. So every review will now be replaced by a 50-dimensional feature vector here. So we define this vectorizer class and we fit that to our reviews, and we also transform these reviews from this text text world to real to this real space, from this text space, so to say, to this real space. And if we run that, you can see that it has converted our vectors to this nice real vectors. And the next thing is now the classification of these vectors. I mean, it says black box classifier, but you already now have some knowledge about logistic regression. So we are actually training simply logistic regression for classification. So it's, I guess, not that much of black box for you now. Anyways, we proceed, and what we do is, just like we loaded the training data, we now load the test data, and again we declare an empty list of test reviews and pre-process all the test reviews one by one and add them to this list, append this list, and in the end we use the vectorizer, this vectorizer, right, which was fitted on the training reviews. We use the same vectorizer to simply transform the data of test reviews. Okay, so we're not doing any training here. The training was done here. The these vectorizer values were learned, and now we simply transform using the same values. We simply transform the test values also, so that both values are in this 50-dimensional vector format. In the end, we learn, like, we import logistic regression, and we fit the data, training data, and now once we fit that, we can predict the probability of test reviews, and this is what is happening here. And you can see that for we have simply printed out for every id its sentiment, and you see if the sentiment is less than 0.5, because this is probability, so if the sentiment is less than 0.5, we will go with 0, otherwise we will go with 1. So it is like a soft classification that we are already provided with as a result of this function of logistic regression class. And in the last thing that is left is to evaluate our results. So for that we use area under curve. So area under curve is actually sort of a way of joining true positive and false positive. You know, it's for instance, we use also F1 metric, where we join precision and recall. Similarly, we use AUC metric, area under curve. Here the way it is made is, we have I guess we have a true positive here and a false positive here. So, like, you know, true positive. I don't know if you guys already know about these things or not. So, in case of binary classification, we have true positive, false positive, false negative, and true negative. So true positive is if it was if the ground truth was also positive and the result is also positive. False positive is if the ground truth was negative, if actually the value was negative and it was falsely classified as positive. Similarly, if a value was positive and it was falsely classified as negative, it is false negative. And if the value was actually negative and we also classified it as negative, then it is true negative. So when we say true positive rate, this means that we are saying that the ratio of true positives to total number of positives. And if when we are talking of, I'm sorry, this is true positive. And when we are talking about false positive rate, this is the ratio of the total falsely classified negative, total falsely classified as positives by actual negatives. So these were the negatives that were falsely classified as positive, and this is the total number of negatives. So these ratios are called true positive rate and false positive rate. Now, one thing that I'm not sure about is whether we have, I mean, we can use on, like, if I have reversed the axis or not. This is something that I'm not sure about. But anyways, so this value can be between this is sort of um, like, this is the box in which the value of AUC can be. So suppose, I mean, just an example. So the more the value towards this side, uh, I'm sorry. for that, actually, I guess AUC. Let's have a look at right now. Yeah, so here it, yeah, okay, yeah, so it is fine. Yeah, so false positive rate is at this side. So we want to have minimum false positive rate and maximum true positive rate, right? So that's why we have something like that. So so this is the area under the curve, right? So this is also a quantization of how good our classifier is. So where were we? I guess, yeah, yeah. Sorry. So we use this area under curve to measure the performance of our classifier, and this is also sort of a built-in metric in sklearns. We simply call this metric with predicted values and compare them with true values, and the area under curve score is 77, like 0.77 or 77%. No, I mean, let's talk in terms of 0.77. And this was end-to-end classification that we have done. And there is another way of doing that. I mean, of course, there are a lot of ways of doing that, but we'll have a look at one more thing, like one more way. And this is using TF-IDF. This is also something that we have looked at during the lectures. This is term frequency and inverse document frequency. So if some term appears exclusively in some of the documents and it does not appear in other documents, then this term sort of becomes really important for classification of that document, right? So for instance, congratulations might be a word that appears a lot in spams, right? And as you have won, similarly, might be some phrase that appears a lot in spams. Okay, so uh, we that's why these phrases or words like that might be very important for classifying spam versus not spam, so to say. So this is the basic idea behind TF-IDF. But anyways, we have already had a detailed look at that in the lectures. So we will simply stick to another way of classification, and that is we will use TF-IDF vectorizer. Before we used count vectorizer, right? That worked by counting. Yeah, count vectorizer that work by counting the presence of different words in different documents, and now we are actually defining a weighted vectorizer that will give weightage to the words that appear exclusively in some documents compared to the others. So again, you can also have a look at this TF-IDF vectorizer. This is also quite detailed, also given in quite detail in documentation of sklearn. I will also recommend you to go through that in detail. And here we follow simply what we were asked in the exercise. So this n-gram range, I guess this is also something that we had a look at during the lecture. So what this means is, like, suppose we have a sentence, hello, how are you? So, in case of n-gram, we actually make a junction, like sort of groups of, let's say in case of 2 gram, we will make groups of two words together, right? So, hello, how is one group, how are is second group, are you is third group. So, this is like a 2 gram model. So that's why we have that's an option, that's an argument that we can give in the function n-gram range. What is the minimum n-gram, what is the maximum n-gram that we want? We'll stick to one here just for comparison with this count vectorizer, and we allow sublinearity also. So again, we use this exactly the same concept that we use for count vectorizer. We use fit transform to train the vectorizer to fit the training data, and then also in the same function we transform the training data to get training vectors, training features, so to say, like real training features from this text space to real space. After that, we have we convert them to array, and we do the same for the test features. And again, so now we again have train and test features in real space, just like we had them uh, we had them here. So this was the test features in real space, and this was the training features in real space for count vectorizer. Now we are using TF-IDF vectorizers, so we quickly transform both the features of training and test set. And after that, we can simply use again logistic regression to fit the training data and output probabilities of the test data. And after that, we can again compare with ground truth values by using AUC, area under curve. And you can see that here the efficiency here, this AUC score is 0.95, which is very good, like quite better compared to 0.77. So yeah, using different approaches can result in different gains in different contexts, so to say. So this lab was about pre-processing of the data, and uh, the main points that we went through were uh, as you can see in on the right side. So we removed the tags, we removed punctuations, we converted to lowercase, we used split to words, we removed unnecessary words, and then we had sort of a clean string of text which was converted to real vectors using count vectorizer, and afterwards using TF-IDF vectorizer. And we learned these vectorizers using the training set, and then transformed both the training set as well as the test set using the same vectorizer. Okay, so the vectorizer was learned using training set, but the transformation was done for both training data and test data to convert data from text space to real space. And once that was done, we simply used logistic regression, and we trained it on training data, and we predicted probabilities of test data. And in the end, we evaluated using AUC score. So this is what we did in this lab. And let's have a look at the next lab now. I guess we still have some 15 minutes, so we have some time, I guess. Yeah, actually, the thing is, next lab is quite related to this current lab, and it is about logistic regression. Okay, so uh, we have already, like, the logistic regression approach is already fresh in our minds. So, and it is quite connected to the last lab, so it makes sense to start this lab at least in this tutorial and see how far we go. Again, I will not probably display this PDF because we have already written the tasks in a Python notebook, Jupyter notebook. So here we will actually implement logistic regression ourselves. We will implement this logistic regression manually. You see, in the last lab, we simply used this sklearn implementation of logistic regression, but now we will use this ourselves. So before moving to that, we first need to come to the same point where we left during the last lab. That is, we, as you can see, like, yeah, we want to use logistic regression implementation by hand. So to come to that point, we first need to do all the pre-processing that we done during the last lab. And you can see this is exactly the same code. So we have this pre-processing function, and what we are doing is we are loading training and test data, and we are first populating this review. In this chunk of the code, we are populating the train reviews list by pre-processed strings of the training reviews, and then we populate the test reviews, clean test reviews list by populating the uh, pre-processed reviews of the training of the test data. And once we have both of them, here we are using count vectorizer, not the TF-IDF. Mm, So we use the count vectorizer, and we use it in the similar settings. Anyways, we have actually increased the number of features here from 50 to 5,000. So this is one thing that we have changed. And afterwards, again, we fit the vectorizer on train views and transform both the training views and test views. So after fitting the vectorizer, we get the features by transforming the strings, and after that we convert this yeah to array. And this we use clean train reviews is equal to none. This is just to free the memory, right? Because this is the last thing that we needed from this variable. After that, we simply free up the memory. So we clean. After fitting the vectorizer, we transform the train reviews and we transform the test reviews. So you see, fit was called only on training reviews. After that, we convert both them to arrays. Like with train data and test data, both are converted to arrays. So yeah, a lot of things are happening in this one piece of code, but these are all the things that we have already seen. So you might remember, I mean, just about 5 minutes ago, we used exactly the same variable like this. I mean, the names were probably not the same, but this train data features and test data features, these were the real features, and we used exactly these features, and we fed these features to logistic regression to get, to get it trained on these training data features and to evaluate the test data features. So, okay, our code is finished here. We can see the shape here, and we can see this training consists of 20,000 reviews, with every review having a shape of 5,000. Now the next thing, logistic gradient. This is something that is interesting and important from practical perspective. So in fact, let's yeah. So before, let's have a look at the sigmoid. Let's review that once again. So this is related to lab 4, I guess, right? Yeah. So we saw that sigmoid of x is equal to 1 over 1 plus e power minus x, and we can also write that as e power x over 1 plus e power x. Okay. So now the problem here is, the thing is, I mean, these both are mathematically totally valid, and like they are just like we can obtain, we can simply divide this by e power x, both numerator and denominator, and we will reach here. So these are exactly equivalent mathematically, but practically we have a small issue. What happens is, suppose we have x is equal to 100. I mean, 100 is not that large a value, so to say. But what happens is, e power 100 might break, uh, let's see, np dot exponent of 100. Okay, yeah, this is still working, but if let's say we have about 150. Ah, cool. It is. Oh, just let me see. So 300. Okay, maybe, yeah. The thing is, they. Most probably NumPy is using some clever, of course, some clever operation to use to calculate this value. Otherwise, of course, we cannot calculate such a huge. Such a huge e to the power 130, it can of course my computer doesn't have this much precision to calculate that. And in fact, you see, like 217, anyways. What I want to say is, if this x grows to a great extent, this becomes numerically unstable. Okay. So in that case, you see, suppose, yeah, in fact, let's have a look at even this case of e power 100. So we have two, I mean, I don't know, let's say 2.68 and something, and into 10 power 43, right? Divided by 1 plus 2.68 and into 10 power 43. So you see, these are very, very similar, right? Right? And there is, I mean, there is very little chance that you will get a good result out of that, because this value is so big compared to 1 that it is nearly equal to 1 already, right? It's really difficult for you to get anything reasonable out of that. Even if we have small like e power 10, this like again we have, it is a bit difficult for us to get something out of that because of this. And we can also land in numerical instability. So what we do is, when x is large, we use this form. Okay. because here we have 1 over 1 plus e power minus x. And here when we have e power minus x, this is numerically very stable, because this value will be uh, like you see like 4.53 times to power minus 5. So this value will be very stable. So when x is greater than 0, the custom is to use this form. When x is less than 0, the custom is to use this form, because we don't want this e power x to explode. So when x is less than 0, e power x is of course small value, and so we can have e power x over 1 plus power x makes more sense. So this is what we are doing here. This is the link to the detail if you want to go through that once again. So what we do is we simply calculate we simply see where x is greater than 0. There we use this form 1 over 1 plus z, and if x is less than 0, we use this form z over 1 plus z. This is the z over 1 plus z form, and this is the 1 over 1 plus z form. This is all we're doing here. And the next thing is to calculate the gradient of logistic regression, right? So here, in order to have a look at that, let me, okay. So actually, this is not so much the gradient of this x itself, but here we have x and y both, and also the weight vector w, as we saw this in the logistic regression case. Actually, what we are dealing here is, you see, in the loss function of logistic regression, we had L of w is equal to summation I is equal to 1 to n. Or I mean, why are we writing this again? Yep, I closed this PDF. Just let me see. I guess here. Yeah. So we have already seen here that this is the derivative. This is the gradient of the logistic regression with respect to w, right? So this is exactly what we want to code here. Okay, and we have already seen that this is this x like e power this divided by 1 plus e power this. This is just the sigmoid form. So this is exactly what's happening here. So here we take sigmoid of uh, okay, maybe let's go through that in a bit of detail, and maybe we'll stop here and continue with the next afterwards. So what's happening here is, actually, if you remember, the function was log of 1 plus exponent minus yi w transpose xi, and we say that this is equal to z. Okay, in that case is a zi, so to say. So this became log of 1 plus exponent minus zi, right? Or if we have a minus, this is just what we just did some time ago. So this is 1 over 1 plus exponent of, or simply write it, minus zi, right? So this is the form of the loss function.
Ryan, sorry.
Yes.
Can you please share the screen? I think you're not showing it. Thanks.
I guess I'm showing you. I'm showing the screen. Maybe. I'm so. Oh, okay. Sorry. Yes, you're absolutely right. Yeah, this happened during the last time also. So, okay. Yeah, thanks for reminding. So, what happens is, we are actually this is the same form of the loss function that we saw in the start of the course. So we are again using the same form of logistic regression. And now, in order to calculate the gradient, we see here we have Yeah, here we have this sigmoid of this thing, right? And this we can see this is what we said that this is equal to z, right? And we can even like neglect b for a moment, because as we saw that in the homogeneous case we can simply include b in w and x also, so we can forget that. So it is it is a sigmoid of minus yi into w transpose xi. Okay, yes, of course I will upload this. So this is equal to y, this is the sigmoid of that. So this is exactly what we will do, and after that we will multiply with yi into xi. So this gradient is equal to I is equal to 1 to n yi xi multiply by sigmoid of minus yi w transpose xi, right? So this is exactly what we will be implementing here. And another way we cannot see the notebook. Oh, sorry. Okay, again. Yeah. So, oh, just a moment. So I was referring to exactly. In fact, I was referring to uh, the same gradient that we have here. Okay. So we are just using the same gradient. I'm just showing you that this thing, exponent of all this thing divided by one plus exponent of all this thing, we can write this in the form of sigmoid. This is just what I wanted to show you. And in fact, if we have a look at this function, we can in fact also write it as uh, I is equal to 1 to n. In fact, if we have a look at this uh, yeah, okay, yeah, we will stick to this first function actually. So this is what we are implementing. And if you now if you see the Jupyter notebook, so this is exactly what we have done here. So we multiply x train and w. Now x train is right now a matrix, and the matrix has the rows are variables and the columns are samples. Okay, so that's why when so it's like having x is it's like having, just let me, yeah. So it's like having x is f is, let's say, feature dimension. X is like that, and of course w is like that. So when we say x transpose, it becomes n into f. Okay, and when we multiply these two, we get n into 1. Okay. So this is what's happening in this part. Okay, and after that we multiply this with y train, because if you have a look at if you have a look at this, to complete z we need to have also this y also. So we have y w, like x transpose w, so to say. Now this thing is ready. After that we take sigmoid of that. That's what we are doing here. So we took sigmoid of that. After that we need to multiply this with x train. Why? When we have a summation here, right? And this summation can be also written in terms of dot product. So that's what's happening here. If we see this x train, this is as we already saw, this is f cross n, right? And we multiply this with y, as we as we can see here. We multiply this xi, this x matrix is multiplied with y matrix, y vector, and we have x into y. And now when we multiply this with this sigmoid, it becomes it takes a dot product of every for every sample with the sigmoid of the sample, and then of course because in the end it takes the summation. Just to show you once again, so this x was f cross n. We multiplied this with this y train, which was n cross n cross 1, and we used this broadcasting, so that now we have x into y. Let's say we have now this thing which is f cross n. And now we had this sigmoid that we already saw. This was equal to its dimension was n cross 1, as we saw here, right? So as a result, what we get is an f cross 1 dimensional vector, right? And every vector, this every dimension of this vector is calculated by a summation of these n samples, right? So that's why, that's how we model this summation in the form of matrix multiplication, which results in the dot product and automatically calculates this summation. So this is what's happening in this g. So this is the derivative of the function with respect to w. This is the derivative of the logistic regression loss function with respect to w. We will stop here, okay? And I will just, if something is unclear, maybe you guys can just go through this form once again. Just look at this numerator and denominator in terms of sigmoid, and you will all it will be totally clear to you how we got this gradient of logistic regression. So we will proceed in the next tutorial with task B, and I guess for now we can stop here. It's already 4 minutes above the time. So if you guys have some question, please let me know. Otherwise, we can say goodbye. Okay, yeah, let's ask assignment one questions after the lecture. But if someone has question related to this tutorial, please let me know. Otherwise, we can conclude the recording. And after that, any questions that you want. Hmm. Okay, it seems that maybe we don't have any questions related to the tutorials till now. So I will stop recording, and I thank a lot you guys for listening so patiently, and I'm sorry once again for taking 5 extra minutes of your time. So goodbye.